Here's a question that sounds philosophical but has enormous practical consequences. When you want data from a database, should you tell it what you want or should you tell it how to get it? These are two fundamentally different approaches, and most developers have used both without realizing they represent a deep design divide. The imperative approach says, here are the steps. Scan this table. Filter for rows where this column equals that value. Sort by this field. Return the first 10 results. IMS and the codicil network model both used imperative access. You wrote code that told the database exactly which steps to execute and in what order. If the database added a new index, your code didn't automatically use it. You had to know the structure of the data and the available access paths, and you had to keep that knowledge in sync with the database as it evolved. SQL took a radically different approach, the declarative approach. You specify the pattern of results you want, the conditions data must meet, the transformations to apply, but you say nothing about how the database should achieve it. You write select name from animals where family equals sharks. You don't write, open the animals table, check if each row's family field is sharks, if yes add the name to a results list. The database's query optimizer reads your query and decides, on its own, the best way to execute it, which indexes to use, in what order to scan tables, how to parallelize the work. This has three important consequences. First, declarative queries are concise. You say more with less. Second, the database can improve its query optimizer without breaking your query stays the same while the execution plan gets faster. Third, declarative queries naturally lend themselves to parallel execution across multiple machines, because you haven't specified an execution order that must be preserved. SQL introduced declarative querying to databases in the 1970s. It was the right idea then. And the next slide shows that the same idea appears in a completely different context decades later. Here's proof that declarative querying isn't just a database idea, it's a fundamental design principle that keeps winning across completely different domains. Imagine you want to highlight the currently selected navigation item on a web page with a blue background. You have a list of items. One of them has the CSS class selected. When the user clicks a different item, the class moves to the new item. With CSS, a declarative language, you write, selected P, background color, blue. That's it. You declare the pattern, any paragraph inside a selected list item should have a blue background. The browser watches for that pattern and applies the style automatically, whenever and wherever the pattern is true. Now try to do the same thing imperatively in JavaScript. You write code to find all list items. You check which one has the selected class. You grab its paragraph child. You set background color to blue. Then, here's the problem: when the user selects a different item, your code removes the selected class from the old item and adds it to the new item. But you also need to remember to reset the background color on the old paragraph, and set it on the new one. If you forget to clean up, both paragraphs are blue. Or neither. The state in your code and the state in the DOM drift apart. CSS doesn't have this problem because you never wrote how to apply the style. You described the condition under which the style should be true. The browser handles re-evaluation automatically whenever anything changes. SQL and CSS look nothing alike. But they solve the same core problem. When you tell a system what you want rather than how to get it, the system can figure out the optimal execution strategy, and it can re-evaluate automatically when state changes. That's why declarative wins. Over and over, in domain after domain. The same principle inspired MapReduce, but MapReduce took an interesting middle road between the two approaches. MapReduce is a programming model developed at Google and popularized by Hadoop for processing large amounts of data in bulk, across many machines simultaneously. MongoDB and CouchDB support a limited form of MapReduce for read-only queries. And MapReduce sits in an interesting position: it is neither fully declarative nor fully imperative. Here's how it works. You write two pure JavaScript functions. The first is called map, it runs once for each document and emits key value pairs as output. The second is called reduce, it aggregates all values that share the same key into a final result. The database takes care of the coordination, distributing documents across machines, routing emitted key value pairs to the right reducers, and collecting the results. The book gives a concrete example. Suppose a marine biologist wants to count how many sharks were observed each month from a database of sightings. The map function checks whether each observation is a shark, and if so emits the year month as the key and the number 1 as the value. The reduce function receives all the ones for a given month and adds them up. The result is a monthly count, no matter how many millions of sightings are in the database. There's an important constraint: map and reduce must be pure functions. No side effects, no additional database queries, no shared mutable state. This constraint is what makes parallel execution possible. The functions can run on different machines simultaneously without stepping on each other. But MapReduce has a usability problem. You have to coordinate two carefully written functions for every query. If your query logic changes, you rewrite both functions and make sure they stay in sync. For this reason, MongoDB later added a declarative aggregation pipeline, a higher-level query syntax that's easier to write and easier to read. MapReduce taught the industry an important lesson: raw power isn't enough. Developers also need expressiveness. The aggregation pipeline is a concession to that reality. And it's a reason why the database world has been moving back toward declarative interfaces even for problems that technically require the computational power of MapReduce underneath.